So today I want to talk about subgraphs. If I have a graph G with vertex set V and edge set E, and another graph H whose vertex set V prime is a subset of V, and with edge set E prime, that's a subset of E, we call H a subgraph of G. And subgraphs are important, an important way of studying graphs, of classifying graphs, and they come up often when we use graphs. So let's look at some examples. We've already seen some important examples of subgraphs. For example, if I have a graph G, let's say the graph that looks like this. So maybe it has vertex set A, B, C, D, E. I might ask, does G contain a subgraph that is a cycle? So in our last video lecture, we learned what a cycle was. A cycle starts at one vertex and then goes via edges from vertex to vertex until it returns to the vertex it started with, and it can't use any edge more than once. So let's see. And it can't use any edge more than once, and the first time it can't reuse any vertices until it comes back to the first vertex. So for example, there's a cycle that starts at A, goes to B, goes to E, and goes back to A. That's one cycle. So does G contain a subgraph that's a cycle? Yes. A, B, E, A is a cycle. Does it contain other cycles? Like we might ask, what is the largest cycle in G? So the largest subgraph that's a cycle in G, let's see, I'm going to use that in blue. Well, maybe we can start again at A, and if we go A to B to C to D to E to A, actually we've seen every single vertex in this cycle. And since in a cycle we can't see a vertex more than once until we get to our start vertex again, this must be the largest possible cycle in A, or because it uses all the vertices. So for example, we could do A, B, C, D, E, A. Has to be a priori just a largest cycle in G, but I think it's actually the largest cycle in G. I mean, of course, you could start at B and do B, C, D, E, A, B, but I think there's sort of one largest cycle, really. Okay, but you could ask for other kinds of things. Like you could ask what's for a path, and you could ask for maybe the longest path in a graph like this. So maybe let's see, where's a path? So a path starts at one vertex, and you don't reuse any vertices and you don't reuse any edges. So for example, a path, let's see, in green, might start at, maybe we can start at A, or let's start at B this time. A path could be like from B to E to D to C. That's a path. I can't make it longer at the end because when I'm at C, to make it longer, I'd either have to go back to B, which would create a cycle, or back to E, which would create a cycle. But I could have made it longer at the beginning if I wanted, like if I started at A. So a path, one long path, and this path is the longest, must be a longest path because it actually uses all the vertices. So, ooh, I didn't want to write that in green. So the longest path in G, or a longest path. So there might be more than one longest path, but no path can be longer than this because it uses all the vertices, is A, B, E, D, C. Another longest path, another longest path might be to start at A and to go A, B, C, D, E. So that one also uses all the vertices, but it takes different edges as we go on this path through all the vertices. Okay, so that's the definition of a subgraph. And we've seen some examples of subgraphs. So what are some important things, properties that we use subgraphs for? Well, for example, a very important definition that we'll talk about later, this is a structure that comes up a lot in computer science. It comes up when we search things, is a tree. So a graph is a tree if it is connected and has no, if it's connected and has no circuits. Remember, a circuit also, like a cycle, it starts and ends at one vertex, goes along the edges. With a cycle, you can't reuse edges, but you can see vertices more than once. So remember this graph, if I look at the bow tie, if I look at the bow tie, then something like this, where I go around like this, that's a circuit, but not a cycle. And the reason it's a circuit is that, and not a cycle, is that I use that middle, I see that middle vertex twice, okay? So a graph is a tree if it's connected and has no circuits. Remember, connected means that I can walk, I can start at one vertex and walk to any other vertex along edges. Okay, so some examples of trees might look like that. That's a tree. Then this is a tree too. Something that looks like this is a tree. Things that look like, let me see, what's another good tree? Oh, something that's just like a path is a tree. And often what we'll do, so these are all trees. Sometimes we'll have a graph that isn't a tree. So G maybe looks like this. So it's not a tree, but we'll ask, is, or does G contain, does G contain a subgraph that is a tree? And contains all of the vertices of G. We call such a thing a spanning tree. So we're going to spend all of next week learning about trees. Here, this is just an example. Maybe because it's a tree, I'm going to draw in green. So here's one tree that's contained in G that uses all the vertices. So I'm going to take that edge, this edge, this edge, and this edge. So those 1, 2, 3, 4 edges, if I take the subgraph that just looks like that, so it looks like that. That's a subgraph of G, and that doesn't contain any circuits. So that's a tree. Okay, so we're going to look for subgraphs that are trees that are contained in G will be important. And sometimes you can use the existence or failure to find the existence of certain kinds of subgraphs to sort of determine, to classify graphs. So one important kind of graph is, let's see if I can get this, are the bipartite graphs. So here's this definition. So a graph is bipartite if there exist sets V1 and V2 that we say partition the vertex set. So the vertex set V is the union of the two sets V1 and V2, and V1 and V2 have no overlap. Oh, let me see, you might not be able to see it. They have no overlap, so their intersection is the empty set. And then every edge in E joins a vertex in V1 to a vertex in V2. And there's a special kind of bipartite graph called the complete bipartite graph, KMN, where the size of the first set V1 is M, the size of the second set V2 is N, and every vertex in V1 is joined to each vertex in V2. So let's see some examples of bipartite graphs. So, for example, this graph, a 4 cycle is bipartite. And how can I see it's bipartite? Well, I'm going to circle these two vertices in red. And I'm going to say the vertices in red are my set V1. So maybe I'll name these vertices A, B, C, D. So the set V1 contains the vertices A and C. The set V2 contains the vertices B and D. And what I can see is that all of the edges in this graph join vertices in V1 to vertices in V2. And in particular, there are no edges between the vertices circled in red, and no edges between the vertices that aren't circled. Okay, so this is bipartite. Trees are bipartite. We'll prove that later. So for example, if I have a tree maybe that looks like this, I claim that's bipartite. I can start at the top here and say, well, this is in is going to be in V1. So the next vertex down can't be in V1, it has to be in V2. I'm going to put these two vertices in V1, and the last two vertices, sometimes we call it, they look like cherries dangling, are in V2. So here, if I name these vertices A, B, C, D, E, F, G, and H, I could say that A, C, and D are in one of the sets, and V2 in the other set must contain B, E, F, G, and H. And I can see there are no edges joining the vertices that I've circled in red, and no edges joining the black vertices either. So this is another bipartite graph. So these are both bipartite graphs. In fact, the first graph is a complete bipartite graph. It's the graph K22. This next one is not a complete bipartite graph because, for example, if it were a complete bipartite graph, then the vertex A would be connected to the vertex, to every black vertex. So A would be have an edge connecting it to E, to F, to G, to H, etc. So this is, not a complete bipartite graph. For example, maybe I'll just say it like this. For example, AE is not an edge, right? And A is red and E is black. So if we're a complete bipartite graph, there'd have to be an edge from A to E. Here is a simple or nice complete bipartite graph K33. Usually when we draw a complete bipartite graph, we'll put the vertices often like in 2 rows. And then it's easy to tell that it's bipartite because you can just do this, right? So here I have the complete bipartite graph K33. Here, maybe I'll draw the complete bipartite graph K23. So 2 vertices and 3 vertices. All right. And one way to tell that a graph is bipartite is the following. A graph is bipartite, I claim, if and only if it has no odd length cycles. Certainly, if it is bipartite, then it can't have what we call an odd cycle. Why? Well, let's just look at it in this example. If I have a cycle, for example, that uses a vertex like this, then it has to go to the other class, but the next edge, so the edges go from V1 to V2, right? So if I start in V1, in the V1 group of vertices, I go to V2, then I have to go back to V1, and you can see that if I started a vertex in V1 and I return to a vertex in V1, I must have gone to V2 and back to the set V1, back and forth, back and forth. So I do it an even number of times, okay? So certainly this direction is easy, and we might see the other direction later. Maybe I'll say easier. It's relatively easy might be not the right kind of thing to say. Straightforward. Maybe I'll say easier. That was better. Relatively easier than the other direction. So if G is bipartite, and a cycle starts at a vertex in V1, it has to use an even number of edges to return to V1. Okay. And that's where that first vertex is, right? So if it's a cycle, it has to return to V1. So here, we can see that we can use this notion of a subgraph to try to figure out whether a given graph is bipartite or not by looking to see, does it have these funny odd cycles? Okay, that's it for right now. Thanks a lot.